This is a video demonstration of a wave generator, so a periodic oscillator, without using any ICs. So over here, I have a constant voltage source, a DC voltage source at 5 volts, no ICs, so hooked up to the breadboard as a power supply. And as you can see, this LED is blinking. So it's supplying a square wave to this LED from a DC voltage source. So how am I doing this? This is called a Astable multivibrator oscillator. And it uses two transistors, two NPN transistors, in a configuration that when one is in cutoff, the other is in saturation and vice versa. And there's time delay introduced by the capacitors to alternate their states. When I was first designing the circuit, I read a bunch of theory on the Astable multivibrator and it made sense. But then when I actually came to build the circuit, there was a lot of confusion as to how the theory would actually convert to the values of the components. So I want to just quickly go over the theory itself and sort of what I learned. The first thing to note is that a Astable multivibrator, the circuit itself, looks like this. So over here you can see that the transistors are hooked up to, so the base of one of the transistors is hooked up to the collector of the other one and vice versa. So ultimately it comes down to this configuration. If we stripped the capacitors and the base resistors to VCC, it comes down to this configuration where we have two common emitter amplifiers with their inputs and outputs hooked up to each other. And what this does is that it creates a positive feedback because the gain of a common emitter amplifier is negative of the RC over the RE. And when you have two of them, it's basically negative times negative, which becomes positive. So if you have a, let's say we put a base, let's say we put an emitter resistor here. If the emitter resistor is large, what happens is the RC over RE becomes less than 1. So it becomes a decaying effect. So it does not cause a runaway. So what happens is if we have a large emitter resistor, and I breadboarded this before, but I'm not going to show that, it runs through these equations that create a equilibrium state at which for example, you can calculate if I had a 5-volt supply and then a 2.2K for the RC and then 2K for the emitter resistor, you can get to an equilibrium state where RC actually just stays at 2.952 volts. And this is actually stable because the gain in the loop gain for one of the transistors to the other, when it gets multiplied, is less than 1. So any small signal passed in through the base does not get amplified once it comes back. And essentially, I'll just quickly run through what this amplification really looks like. So when the RC over RE ratio becomes bigger than 1, what happens is, let's say a small signal comes through RB. This will, let's say it increases a little bit of voltage in this base resistor. This base emitter is going to increase in voltage, and then the current through the base, in the emitter is going to increase by V over RE. And then this current is going to come from the collector, and the collector current is going to drop RC to below where it used to be. So it's going to have a negative gain, basically negative. So AV would be equal to minus RC over RE. And then what happens is this gain gets transmitted along the collector output to this transistor. So now this transistor, when this transistor goes up a little bit, this transistor goes down a lot. And when it goes down a lot, the opposite effect happens here and it pushes this collector up a lot. And then it's going to feed back into this transistor, and it has like a runaway effect where tipping one over will increase the other one. So what happens if we actually just create the circuit with a positive gain? So what happens if, let's say, this emitter resistor is small compared to the collector resistor? What actually happens is when we calculate the stable state, the equilibrium state, so you can derive that by basically equating the voltages of the collectors and the emitters, and basically make sure that this voltage drop is the same as this voltage drop. So the collector emitter, sorry, sorry about that. I'm just trying to see what that means. Oh yeah. So basically, if we set the collector base voltage drop to be the same across both transistors, you can find the equilibrium state, and it's unstable for a configuration with a positive gain, with a gain bigger than 1. So then what actually happens is, in that case, is it starts to swing, and then it finds an equilibrium state in a point where the gain becomes 1 again. And the reason why it does that is because one of the transistors become very close to saturation, and the other one becomes very close to cutoff. And it's going to be basically, one is going to be above the above the equilibrium collector voltage, and one's going to be below that. And essentially, a common emitter configuration will always go through a gain of 1 as it comes close to saturation and as it comes close to cutoff. That's because the emitter current is ultimately decided by the Shockley diode equation. I'm not going to go too far into that, but I think it's intuitive that, at cutoff and at saturation, the gain is exactly 0. So therefore, there should be a transition point where they're very close to cutoff and saturation, where one is above the equilibrium voltage, one is below, where it becomes exactly 1 in the gain, and therefore stabilizes. Therefore, any change will decay back to the original stable voltage. So in this case, I actually found that when I was using a 2K for the collector resistor and a 1K for the emitter resistor, therefore there's a gain of -2. The calculated stable voltage is 2.13. So the calculated equilibrium voltage is 2.13. So if it's an equilibrium, we should see both collectors having a 2.13 volt across them. But I didn't see that. In fact, they varied quite a bit. So one was at 2.3 and one was at 1.9. Basically 0.2 volts above and below the equilibrium voltage, which makes sense because one of them were close to saturation and one is close to cutoff. So what happens if we keep dropping this emitter resistor? So there's a point where you can drop it so much that the current through this path, so the current through the collector of transistor A into the base of transistor B out the emitter of transistor B, you can drop this resistor so much that this path can no longer push this voltage into saturation. So, for example, if this was 1K, let's say 2K ohms, and this was, let's say, a very small resistance, let's say 0 ohms. I'll take a very extreme case. What happens is when you put 5 volts through this, this is going to drop 0.7 volts, right? Let's say it's in saturation, because we want to see if it can actually exist in this state. Let's say it can. It's 0.7 volts. And then this is going to have 5.7. Oh, sorry, this is going to have 4.3 volts across it. And it's going to basically say that the current through this is uh, IC is going to be 4.3 volts over 2K. So it's going to produce some sort of current. But notice that essentially this state just cannot exist, right? Because so the reason why it can't exist is it can only exist for one of the transistors. Suppose this is 0.7 volts, like this dropped across here. What happens is this pushes this transistor into saturation, and because the base is at 0 volts, the collector is at 0 volts. My bad. Because the emitter is at 0 volts, because it has no resistance, there's no voltage being pushed up by the resistor in the emitter. In saturation, the collector is going to be at 0.2 volts, right? Because it's just 0.2 volts above the emitter voltage. And therefore, this base is going to be at 0.2 volts. So this base is going to be a cutoff if this exists in saturation. And so you come to a state where if the emitter resistor is too small, it can no longer raise the base voltage such that to maintain a 0.7 volts base emitter voltage drop, the other transistor has to go into cutoff. And this becomes kind of like a flip-flop in which one of the transistors will always be in cutoff and the other is always in saturation. And you can switch the state of them by basically jumping the base voltage above the cutoff base voltage. And I breadboarded this, and this actually is true. So if you strip away everything in the Astable multivibrator, you end up with a flip-flop that stores the two states, one in cutoff and one in saturation. So then why do we need everything else in the Astable multivibrator? What is it actually doing? Okay, so if we didn't have these base resistors to VCC, the base that stays in saturation will always just stay in saturation, and the base that stays in the transistors that stays in cutoff will always just stay in cutoff. So by supplying these base resistors, we ensure that there's some mechanism which could flood the base with current again to bring it out of saturation. And I'll show why that's important in a bit. Next is the capacitors are added to create the time delay. So if we didn't have them, the circuit would reach a steady state essentially with both of these bases out of cutoff because of the base resistors. But by adding the capacitors, any wiggle in the supply voltage will cause one of them to be biased in one direction and the other be biased in the other direction. And therefore, it creates this sort of square wave. And I'll go through actually what's going on here. So at time t equals 0, let's assume that this transistor is on, so this T2 is on, and this transistor T1 is off. And what happens is the voltage across the capacitor at this point is 0.7 volts facing this transistor because it's tied to ground through the base emitter PN junction. And then the opposite side of the capacitor has a voltage of minus VCC plus 0.7. And I'll tell you why that is in a bit. Because once we get to the next part of the cycle, we can see why. So at t equals 0, the voltage across VCC is Sorry, my bad. Yep. The voltage across this capacitor actually is VCC on one side and 0.7 volts on the other side. My bad. So that's why at time equals 0, the V out of this one, you can see is 5 volts. However, on the other capacitor, it's actually the opposite. So on one side, because this is on one side, it's 0.2 volts facing this end, right? Facing the collector, which is in saturation. And then the other side is minus VCC plus 0.7 volts, which I'll tell you why in the next cycle. So what's happening is this is a negative voltage, which means that it keeps this this transistor T1 in cutoff. But there's a wire connecting the base through a resistor to the supply voltage. And so it charges this capacitor through this base resistor. It's basically a series RC circuit now, right? Because it's charging through the VCC. And after it charges up to 0.7, charges this plate up to 0.7, this transistor turns on. So that becomes at T equals tau. So this transistor turns on. This base now drops from VCC to 0.2 volts. And therefore, the other plate of the capacitor will decrease to minus VCC plus 0.7 volts. And the reason for that is because the voltage across capacitors cannot instantly change. It takes time for it to change. So once this transistor turns on, that voltage difference is basically added to this plate. And then this plate instantly shuts off this transistor, T2. So it turns off this transistor, but when it turns off this transistor, this voltage supposed to drop to 0.2, but it does not drop this plate to 0.2 immediately because the transistor is turned off, and this plate needs to charge up through the resistor RC here, and this resistor is large. So therefore, what you actually see is you see a trailing, you see an instant shutoff of the voltage as the transistor turns on, and you see a sort of curved edge as the transistor turns off, and the voltage sharply increases. So that's what's going on, and so that's why on my breadboard, you can see that the light turns off basically immediately. I'm not sure if it's capturing that in the camera, but it's turning on like kind of slowly, right? It's turning brighter and brighter, and then it shuts off instantly. So that's what you see with that. So then lastly, I want to just talk about how do I calculate, how do I define the values of the resistors and the capacitors. And this was counterintuitive because so I used some equations to do this, but for some reason I'm not seeing the results on my breadboard. So theoretically, I'll just go over the theory of how to do this. So in theory, your base resistors need to be smaller than the collector resistors times the beta value of the transistor. And the reason is because in saturation, the current through the transistor, right, it's going to be basically VCC divided by R1, because the transistor collector to emitter voltage drop is only going to be 0.2. So the saturation current needs to be supplied by, the base current needs to be able to supply the saturation current through the CE junction. So therefore, the base current needs to be bigger than whatever the saturation current is divided by the gain of the transistor, the HFE value or the beta value. So that's the one thing. That's one thing you have to decide. For me, initially I picked R1 to be 2K, and then R2 to be 20K, and that worked. It drove the transistors in saturation, but then it didn't allow the transistor to hit cutoff, which is very strange. So somehow, if the R2 value is too big, um, uh, uh, yeah, for some reason, when R1 is too small, R2 is too big, but not big enough to not allow it to go into saturation. There's a state where it can't actually hit cutoff. So instead, what I did was I used R1 as I believe 6.6K, and R2 was 20K, and then it can actually hit both cutoff and saturation. And the reason is, I believe, because this capacitor, the capacitor that's connected to the base resistor on one side and the collector resistor on the other side, if it charges too quickly, which will happen if R1 is too small or R3 is like too big. Sorry, yeah, or vice versa. Whatever, I don't quite remember, but there's a configuration where I think if the capacitor charges too quickly, it never actually hits cutoff, so it prevents the circuit from actually hitting cutoff. The next thing is to notice this capacitor actually switches polarity during the cycle. In one side of the cycle, it's positive towards the collector, and on the other side of the cycle, it's positive towards the base. So using an electrolytic capacitor is not the best idea. However, I needed the electrolytic capacitor because I needed the large capacitance in order to create a time delay long enough to be visible. So lastly, I just want to say that in order to calculate the time delay, it's essentially just a RC charging circuit. So with capacitors, the current across a capacitor is equal to the capacitance times the change in the derivative of the voltage across the capacitor divided by time. And if you use this sort of differential, this sort of derivative relationship between the voltage and current across a capacitor, you can derive the equation which defines the voltage across the capacitor at any time t. And the circuit that we're really looking at is essentially there's some voltage supplied by the base resistor at 5 volts, and then by the collector at 0.2 volts because it's in saturation. And then the capacitor has one plate that is at minus VCC plus 0.7 on one side, and then 0.2 on the other side. And there's a base resistor here. So it's essentially a series RC circuit. And it needs to charge up to a state where the side facing the base becomes 0.7 volts. So you can sort of find out this relationship and then sort of do a bit of math and find out that for some value, so I'm using 20K for the base resistor, I first used 22 microfarads, which gave a 33 millisecond time for the charging. And then I used a 470 microfarad, and it gave a t equals to, I think, about like 6 seconds or something. The reason why you don't see this LED flashing at 6 seconds, it's kind of doing it every second. So every half a second is the charging period. The reason why you don't see t equals 6 seconds here is because by adding a LED in parallel to the collector, it's making sure that the collector voltage never exceeds the LED's forward voltage drop. So instead of going all the way up to 5 volts, it's only going up to the LED's forward voltage drop, which should be about 1.7 volts. So that's why the charging time is so much less. Because here, instead of it being 5 volts being the voltage supply, so instead of this being 4.8, it's essentially 1.5. Yeah, so that's why it drops it so much. Um, all right, that's it. So this is the Astable multivibrator. Just having a look at this again. It's pretty cool. The circuit has no IC components. It's supplying a DC voltage, and it's able to create an oscillation. Thank you.